What are we trying to do? We're trying to find the limit of the Riemann sum, to find the exact area under the graph between 0 and 2. 3 preps. The first prep is delta x, which is the width of each subinterval. Remember, we have n subintervals. Subintervals. And eventually n will go to infinity. So the width of each subinterval will be b minus a divided by n subintervals. So 2 minus 0 over n, or 2 over n. Prep number 2. xi. So let me go back here and just show you what I'm trying to do first. This is my first prep. This is my second prep. And this is my third prep. And then I will put all pieces together to determine the limit of the Riemann sum. But I can't write this. There is no point. Before I determine this piece, and then plugging in the function. Okay. So now let's illustrate this interval. This is the interval 0 to 2. And imagine the function is up here. So this is my first subinterval. The width is delta x. This is the next subinterval. The width delta x, and I get x2. Here is the third subinterval, delta x, and I get x3. Dot, dot, dot. xi minus 1, xi, xi plus 1, dot, dot, dot. xn minus 1, and the last one is xn. All these have delta x. All these delta x everywhere, delta x. So the starting point is 0. How do I get x1? Oh, okay, it's 0 plus delta x. How do I get to x2? No problem. It's 0 plus twice delta x. How do I get to x3? Well, no problem. It's 0 plus 3 delta x. I don't care for any of these. I care about xi. So how much is xi?
I delta x?
Yes.
Well, 0 plus
exactly,
I delta
perfect.
x.
Yes, I delta x. I have delta x 2 over n. So it's I times 2 over n, and we like to write it as 2i over n. So I got delta x, I got xi, and the third prep is f of xi. In this function, I plug in xi plus 2. So 2i over n, everything squared plus 2. I squared, I get 4i squared over n squared plus 2. I have all my preps. Everything is ready. I can start to put. I can put together the limit of the Riemann sum right now. So the exact area, no approximation whatsoever, no error, nothing, is the limit as n approaches infinity from the sum from I equals 1 till the last subinterval from delta x 2 over n multiplied by f of xi, in parentheses 4i squared over n squared plus 2. At the end of our calculations, we will get the exact area. Okay. Some time ago, we wrote the properties of the summation notation. There are 3 properties. If something does not depend on I, it's just a constant, does not have I in it, and it multiplies the general term, goes in front. let me leave this because I'm going to refer back to it in a minute. Perfect. Okay, this doesn't depend on I, has nothing, no I in it. I'm going to put it in front. Limit as n approaches infinity 2 over n. Now I'm going to use a different property that says the sum of the generic term plus another generic term is the sum of the first one plus the sum of the second one. So the sum of this plus the sum of this from I equals 1 through n, from I equals 1 through n. At this point, I notice that this is a factor in front of I squared, and this is a factor in front of 1. So I'm applying the constant rule. So limit as n approaches infinity 2 over n. You cannot take anything outside of the brackets just yet. So just in front of the summation notation, 4 over n squared, the sum of I squared, plus 2, the sum of 1. I know this and I know this. I remember them. This will be replaced by the ugly one, n plus 1, 2n plus 1 over 6. And this will be replaced by the nice one. So now I continue. Limit as n approaches infinity from 2 over n. It's still in brackets. 4 over n squared times this, n plus 1, 2n plus 1 divided by 6 plus 2n. And close the bracket. I'll try to simplify a little bit. I can. Tiny bit. By n and by 2. So then limit as n approaches infinity from 2 over n. I realize that the least common denominator is going to be 3n. 2 will multiply this, but I'm going to distribute them. So then 2, this is not the same 2, this is this and this is this. So 2n squared plus 2n plus another n is 3n and plus 1. But since the denominator here is 1, but the denominator, the least common denominator is 3n, I have to multiply this by 3n plus 6n squared. From this moment on, I just clean it up and I get the area. Limit as n approaches infinity. Of course, the denominator becomes 3n squared. Leave the 2 alone for a moment. So 2 times 2 is 4n squared plus 6n squared is 10n squared. 2 times 3n is plus 6n, and 2 times 1 is 2. We know the answer from pre-calculus, but let's say we don't remember. So I have limit as n approaches infinity. I'll distribute the 2. 20n squared plus 12n plus 4 over 3n squared. And we know that it's infinity over infinity, and we have L'Hopital's rule. So limit as n approaches infinity from 40n plus 12 over 6n. Again, infinity over infinity, and we get 40 over 6, or 20 over 3. Exact. No error whatsoever, because we divided everything, the interval, into n subintervals, and furthermore, we made n go to infinity. So the minimum, the lower bound that we got with the leftmost point, I think it was 5. Yes. So it was 5, the midpoint was 6.5, and this is 9. How much is this? Not too far from that. And we only use 2 subintervals, right? So that is what, 6.6666666, and this is 6.5. You're going to see in Calc 2, you're going to approximate integrals, because you are not going to be able to determine the antiderivative for any function. I can give you, for example, a function that no one can find the antiderivative for. So for this function, no matter what you do, you're not going to find an antiderivative. Other than using Mathematica or Maple, you will not be able to find by hand an antiderivative. But you can still find an approximation of the area under the graph using such and such rectangles or trapezoids with the trapezoidal rule. You can still determine the area. An approximation. Okay, so let's choose another function, linear, quadratic, or cubic, and illustrate the limit of the Riemann sum again. Any preference? Since I will not talk about integrals today, but since I put the title in there, what is the connection between all this and the integral? So the area, exact area, which we know now is the limit, so now we are going to use the Latin S, but elongated, stretched, for our convenience. We're not going to do this moving forward. We're going to do this, but there is no time to even talk about this today. So this is the definite integral that gives the exact area. So of course this is on the interval a comma b. This is on the interval a comma b. And what do you see here? Identical. That's why, remember, we said this is the exact difference in x, and this is the differential of x. But everything else is the same. The limit and the sum are together in here to give us the exact same answer. Okay, so I don't know if we have time, but let's choose any function and go through the limit of the Riemann sum again. Let's choose a function you like. If we want us to finish in a few minutes, we can use a linear function. If you don't want to finish at all, we can choose a cubic function, and it will take us some time. If you want to be nice, you will choose 0, comma a number. If you don't want to be nice, you can choose 2, comma 5, and you mess us up for a long time. But we have to see at least another example now and one on Tuesday.
Maybe a linear.
Okay, very good. So let's look at a linear function. The areas under graphs could be positive or negative. We don't have to discuss this right now, but for example, we can have this situation. This is a positive area, this is a negative area. The total area will be positive. But we can have this situation. This is positive and this is negative, and the answer will be negative. Okay, so would you like to choose a linear function? And I'm getting a sip of water.
The question for those illustrations you made there.
Yes.
Would you kind of break it into 2 parts and then just
no, there is no need. When we find the definite integral, there will be no need.
Okay.
You will see the technique then. But if you're referring to a property, the indefinite integral has a lot of properties. But if you're referring to this, yes, you will have the integral from 0 to 10 from f of x dx. Yes, you can write it as the integral from 0 to 7 from f of x dx plus the integral from 7 to 10 from f of x dx. Yes, this is one very important property of the definite integral. We're going to discuss this when we talk about definite integrals. Definitely. So let's choose a linear function. What about 2x plus 4? And we can make it slightly more difficult. Let's say the interval between 1 and 3. I need the 3 preps first. The first prep is delta x, which is 3 minus 1 over n. I don't want you to think that we will always get 2 over n, so let me change this into 5. I don't want you to get that impression. So 5 minus 1 over n is 4 over n. Okay, so xi, this time xi is 1 plus I delta x, which is 1 plus 4I over n. This is what I have to plug in x, or replace x by. So f of xi is 2 in parentheses 1 plus 4I over n and plus 4. So this is 2 plus 8I over n and plus 4, which is 8I over n plus 6. I have all my preps. They're all done. Now I can write the area, the exact area, under this graph between 1 and 5, which is the limit as n approaches infinity from the sum from I equals 1 through n from delta x 4 over n times f of xi 8I over n plus 6. Like before, and moving forward, you can already put this out between the limit and the summation notation if you want to save time. So limit as n approaches infinity from 4 over n. Now I have the sum of two terms, so it is the sum of 8I, in brackets, don't forget, because this has to be distributed to both. So the sum of 8I over n plus the sum of 6. And this will be limit as n approaches infinity 4 over n. Again, I take 8 over n in front, and I will have the sum of I, which is nice, n plus 1 divided by 2, plus, this is 6 times 1, I take 6 in front, and the sum of 1 is n. See, it took me 40 minutes to explain the first function, and it takes us 4 minutes, 5 minutes to, but of course also it's a linear function. So limit as n approaches infinity 4 over n, I'll try to simplify by 2. So in brackets we have 4n plus 4 plus 6n, and this is limit as n approaches infinity 4 over n times, this is 10n plus 4. And this is the limit, n approaches infinity 4, 10n plus 4 divided by n. I should have distributed already. So this is limit as n approaches infinity from 40n plus 16 divided by n. When I differentiate, the top will be, because it's infinity over infinity, when I differentiate, the top is 40, the bottom is 1, so it's 40 units. So the area under the graph of 2 2x plus 4 between 1 and 5 is 40 units.